Good afternoon, everyone, and welcome to this new CONSELF webinar. My name is Alessandro Palmas, and today I will show you how to use CONSELF Cloud Simulation Platform to simulate flow in urban contexts. Before we start, I just want to remember you to log in with your Google account before joining the session in order to be able to ask questions in the live chat. So, a few words about CONSELF. We are based in Milan, in Italy, and we have few headquarters in Italy and other regions, but we also have a worldwide distributors network that covers basically from the Far East to the Latin America regions. So, as you can see here, we started our webinars in April, and they are continuing through May up to the next week when we will have the stress analysis webinar on May the 19th. Here you can find our references, and if you need any information, you can write us at info@conself.com. And in order to stay tuned with our updates, I strongly suggest you to follow our LinkedIn page. A few words about what we do. We have three different services that we provide. The first and most important one is the simulation platform on the cloud. That is the one we're going to talk today. It's a complete simulation platform available through a simple web browser. Then we offer also a cloud computing service with a pay-per-use approach. We provide all the computing power you need on demand. We also provide engineering consulting to optimize your product design and also to make available simulation technology into your design workflow. So let's start to talk about the case we are going to see today. And here you find the geometry we are going to deal with, and also a few key aspects we are going to analyze. So starting with the geometry, you see here on the right side depicted the simulation domain. It consists in basically a set of buildings, a simplified geometry of a modern city area with few skyscrapers and also small buildings together in the red surface zone. Then we will put all these buildings inside a domain that basically is the portion of space surrounding our environment and our cities that we are going to simulate. So we will make the wind entering this domain from the inlet with a uniform profile of coming from the inlet and directed towards the outlet. We have also two lateral boundaries that are in light green. Finally, we have the ground in dark green and the ceiling in light blue. We will see through the simulation setup how these different surfaces are going to act in the CFD configuration. And so we will learn how to express all the concepts that we have in mind, like the ground, how to simulate the ground, and so on. So let's focus on what type of insights will this analysis make available. So basically, we are able to see how pressure and velocity distribution are obtained when the wind interacts with our buildings. And so we can evaluate the pedestrian comfort as well as the pressure loads on our buildings And we will see also a very nice picture that show us the path of a contaminant that is released from a contaminant source inside our city, and we will be able to find out how it will be dispersed by the wind in our environment. When dealing with this kind of simulation, there are some advanced aspects that will be not part of this webinar, but they are listed here because they can play a major role and they need to be taken into account. Let's say mesh resolution is a very important aspect, since you have to be sure your mesh catches every flow structure, especially when dealing with turbulent flow. But also, you cannot use cells so small to catch every single feature, because this would need too high amount of RAM in order to run your calculation. So this is a classical trade-off you're gonna face. Also, another important aspect is the velocity inlet profile. We will use a uniform profile, and but there are a lot of nice other kind of inputs that the user can use, and we will make these inputs available very soon on our platform. Another aspect that we will have probably next week is the surface roughness. That is a feature that on which the velocity on ground, on the wall surface depends. Then we have solar radiation that should be taken into account when dealing with natural ventilation, as well as porous surfaces and humidity and evaporation that are key factors, and also power sources, for example, traffic. So this is a brief summary of what we will see today, and now we can start to use the platform to complete the whole simulation cycle from CAD upload to result post-processing. So as I told you, the platform is a web-based application and is completely accessible through a simple web browser from an internet-connected device. So let me just switch from my presentation to a browser. Okay, so now we are on the CONSELF homepage. That is the place where you should start every single simulation you will complete. So in order to register, you have to go to the login button on the top right of your screen. And here you can log in or register. Okay. If in case you don't have your own account, you have to insert an email and a password or use the social login. I already have my credentials, so I can just hit the login button. And the thing that happens, you are redirected to the dashboard. That is the web application main page. On your account, on the very first login, you will have 0 credits. And so you will have to activate your welcome plan that gives you simulation credits, and so that you can start your simulations. In order to do so, you have to go to the My Account page and complete the checkout through the store. Store by, choose the product, that is the Cloud Simulation Plan, and sign up for the welcome plan. That is completely free. It gives you 20 credits per month, and it's renewed automatically at zero charge. Once you check out the welcome plan on your dashboard, you will see you will have 20 credits every month. There are a few tabs on the left menu. The first one is the dashboard that has some statistical data about your account. Then there is the simulation tab, where you can create a new case, open an old one, or look at the cases that are in progress, that are running on your account. Finally, there is the storage tab that shows you the space, the amount of space you have occupied by your simulation, with some statistical report on the right. And finally, on the bottom of the page, you have the entire list of your cases that you can manage deleting them in order to free some space. As a final remarks, as you can see on the right part, on the left part, sorry, you can see on the bottom there are two different buttons, and one is in order to contact support, and the other one refers to the user manual. If you click on it, the manual will open on another window, and this is a very important document that guides you through the complete setup of the simulation. It gives you a detailed description of every parameter you are requested to insert during the simulation setup. So refer to this document in order to find out what a particular parameter mean or do. So let's get back to the simulation, and we are ready to start our case. The first thing to do is to choose an application. As you can see on this select, you have quite a few choices, and we are going to add a lot of new dedicated application here in order to make it very easier to our customers to choose a dedicated specific environment where to set up their simulation. In this environment, you have only to deal with familiar parameters, because these are parameters of your area of expertise. And so it will make simulation, CFD and also stress analysis simulation very, very simple. In order to create a case, once you select an application that for our case is a general one, you have just to insert the name and click on create. So as you will see, the whole simulation process will be organized in 5 or 4 steps, depending on the application. And they are listed here on the top of the window, right after your case name. So the first step is the geometry one. We are gonna update our file, and we're going to interact with it a little bit in our graphical window. And in order to upload the file, just click on Upload File Now and select your geometry. CONSELF Cloud Simulation Platform allows to use STEP, IGES, or STL files. In this case, we uploaded a STEP file that will be shown on the right part of our screen. And here it is, our geometry displayed on our screen. So this graphical window allows you to interact with the mouse. With the left button, you can rotate the geometry. Right button, you can zoom in and zoom out. And clicking the middle mouse or both left and right, you can move the geometry around. In order to reset the center of rotation, you have to double click on the point where you want to reset to be resetted. So right now, we have to start to assign some values to our parameters. The first thing to do is to define on which unit of measure our geometry file is. In order to find out, if you don't remember, you can take a look at the information of your geometry and see that the sizes of your geometry are reported Here, as you can see, X, Y, and Z are in appears to be in millimeters. So the default choice of millimeter is okay. We can click next and go to the second section of the step geometry. Here we have to choose the flow type. It can be either internal or external. It's quite straightforward to identify this flow as an external flow, since the external part of our buildings are going to interact with the wind arriving from the inlet. So this is an external flow. Once you choose external, you have to add 6 parameters that defines the bounding box. And these parameters are basically the values, the delta values between where your bounding box side has to be placed with respect to your geometry. For example, the most simple one is the minimum bounding box in Z direction. So the ground, the side that is going to play the role as the ground. Since our buildings will be placed right on top of this ground, the delta in the Z direction should be 0. Be careful that in this case you have to insert these values in file units. So we saw our geometry was in millimeters, and so these values must be specified in millimeters. The span of our geometry, the sides are 229 meters in X, 140 in Y, and 75 in Z. So in order to define a good bounding box for our geometry, we can use deltas in X and Y that are of the same size of the geometry bounds. So X we saw was 230 meters, so we have to add 3 zeros on the X. Same thing for the X plus. And for the Y, we had 140 millimeters. And we are going to add them 2 here. And about the Z, we have 75 meters buildings. Okay, the tallest one should be around 75 meters. So we can add to 75 other 50 meters in order to place our sky, our ceiling. So we are almost done. We just have to define the boundaries on our geometry. We want to group the whole boundary, the whole geometry together in one single boundary. We can do it by clicking in the selection, select here, and choose select all. This will highlight every single surface of our geometry. And at this point, we can create a new boundary and name it buildings. Okay, so at this point we have a new boundary called building, and we will have also 6 other boundaries that are the sides of our bounding box. At this point we can just click on submit and confirm. Every time you click on submit, a new process appears in the bottom section of the simulation tab, showing you the progress of your process you just launched. And once it completes, then you can open your case file from the selection of cases section. The geometry step is very quick, and so in a few seconds we will be able to open our file in our selection of case. Okay, we are ready to go. We could just click open, and as you can see, the simulation proceeds from geometry step to Mesh 2D. From Mesh 2D on, everything, the first thing we have to do is to select one entry from the menu Start From step. Here you specify from where to start your process. We just run geometry step, so this is the single entry we have. In case you run multiple steps, you will have here a few choices, but the first thing to do is to choose the one where you want to start from. Loading the geometry step, you see we have the bounding box together with our buildings. And so, as you can see, we created a domain around our buildings, so we can proceed with our meshing phase. In order to specify a good meshing resolution, we have to take a look at the geometry information. As you can see, in the geometry step, we converted our unit from millimeters to meters. So from now on, the software needs only quantities in the international system. So for the length measure, you have to specify the number in meters. You have to do just one thing in surface mesh, and is to prescribe for every single boundary you define. So you can see here buildings and then all the bounding box, 2 parameters. These parameters are well explained in the manual, and they basically rules how this first one rules the difference in sizes allowed as a percentage. If you want 100% uniform triangles, if you put here 99.9%, you will obtain equals triangle on a given boundary. So 70 for us is a good, it's the default choice, and it's a good measure for this case. Then we have to specify the mesh size. So this is basically the characteristic length of our surface element that is a triangle. And we saw that our buildings are 75 meters tall, so 1 meter can be good enough for the building. For all other boundaries that are the bounding box, 5 meters can work too, since the bounding box it's quite bigger with respect to the building. So 5 meters is okay. You have to specify this value for every boundary. And that's basically all for this section. Just keep in mind to verify that every boundary has the number you want. And so 5 is the number for every side of the bounding box. Now we are ready to go. We can hit submit, and the mesh 2D, that is the surface mesh, is ready. So in order to save some time, I already run this step, and I'm going to open the case that is already run in order to save us a few minutes, but the process is the very same. So let's go back to the tab simulation, open the case named buildings that I already prepared. So at the end of mesh 2D, you have the mesh 3D. Again, the first thing to do is to select the step from where you want to start. Here, mesh 2D just run, and we will see in our graphical window how the surface mesh appears. So, as you can see, we performed a surface meshing on our bounding box, and also hiding these boundaries with a button. We can go inside and take a look at the meshing on the buildings. And as you can see, we have 1 meter triangles describing our surface on the buildings. Okay, so it's good enough. And now we have to choose the volume mesh algorithm. At the moment, we provide 2 different algorithms, and one is the tetrahedral with boundary layer, and the other one is the hexahedral. For this particular case, we are going to use the hexahedral one. So just select it, and then assign this parameter, that is the max element size. Basically, it gives you the dimension of the the largest element you will find in the domain. And if you remember, we select 5 meters for the bounding box. And so we can prescribe to have 4 meters wide as the largest dimension for our cells inside the domain. Then we can just click next and go to the boundary treatment section. This section has 2 different behavior depending if you are in a hexahedral meshing phase or in a tetrahedral one. For the hexahedral, this boundary treatment rules how to refine the mesh in the vicinity of our surfaces, as well as the number of layers of cells of the same size you want to have in your domain. So again, you have to select every single boundary from this menu and choose a number of layers and the cell dimension. We are going to see in our manual what's the meaning of these 2 parameters. So going in the manual, you can just click on the Mesh 3D phase boundary treatment. And here in these images, there is represented the 2 different type of algorithms and how the boundary layer acts in the 2 different situations. So when you choose the hexahedral mesh, you can see here that the layer number defines how many cells you want to place one near the other one before allowing for coarsening, while the cell dimension is the dimension the cell has to have near to the particular surface. So in our case, we can define this parameter for the buildings, prescribing 5 layers and a cell dimension of 1 meter. Okay, so we can do the same thing for the bounding box Z minimum, that is the ground, and we want, again, 5 layers and this time 2 meters on the ground. For every single boundary, remaining boundary of the bounding box, let's say X min, X max, Y, and Z max, we can leave the default values of 0 layer number. This means that the value of the cell dimension will be ignored and the values prescribed in the previous section, Mesh 2D, will be used to prescribe the refinement. So basically what we are saying is that on the buildings, we want 5 layers with 1 meter for the cells, and this is also true for the Z minimum with 5 layers and 2 meters. So it's important to prescribe a good refinement for the ground, since it's a no-slip boundary too, and you have to prescribe small cells near it. Okay, so we are good to go. We can click on Submit and start the 3D meshing phase. Again, I'm going to jump to the result in order to save us some time, and we will see it in the CFD phase. Okay, the next step is the CFD. And again, the first thing to do is to load the previous step, that is the Mesh 3D we just completed. Now you will see a slightly different graphical window will appear, because this one will allow us to perform few different manipulations on our mesh. And so we will see that now this is our domain that has been meshed inside. And the first thing we can do is to open the menu with the top left button, highlight our file, and click on the information. As you can see, we have 1,000,000.6 cells. So another thing we can do is to color the domain by mesh quality. This is a parameter that describes the quality of our mesh. It basically has 2 different values, 0 or 1. Where you find 0, the cell is good. Where you find 1, the cell has some problems in terms of accuracy that will impede a good CFD solution. So you have to highlight those that have one value and identify the zone of your mesh that require a higher refinement. If you click on the tick here, the mesh colors by the mesh quality value, and clicking on the range, we can see that our value, mesh quality, ranges from 0 to basically 0 again. So this means that the quality of our mesh is everywhere okay. Now, if we want to take a look inside of our mesh, we have just to highlight the file, click on the plus here, and then choose a clip and place maybe this clip along the y direction. Then choosing a representation with surface with edges so that we can take a look at the cells we have inside our domain. Okay, hiding the menu with the same button as before, we can zoom in and take a look at our mesh in the proximity of our buildings. And as you can see here, we have the cells describing our geometry. Okay, so we are ready to proceed with our CFD setup. In the first section, fluid models, we have to choose the fluid model and the turbulence model. Fluid model is incompressible. Okay, we are simulating air, but at this speed, the fluid behaves as an incompressible fluid. As a turbulence model, you find in the literature that for environmental simulation of this type, the K epsilon is a typical choice. The density is, we can assume, a classical value of 1.225, as well as for the viscosity. Then we have the fluid and turbulence initialization, and we can leave the default value since we are going to simulate the pressure that we have in the standard condition, so 1 atmosphere. This section is complete. We can proceed to the boundary setup. Okay, boundary condition, we have to prescribe a boundary condition for every single entry of this menu. Starting with the buildings, we know that we want to simulate them as walls, particular no-slip walls. And so the default choice is OK. Same thing for the Z minimum, that is the ground. This is a wall no-slip too. OK, let's start to add the wind movement. And so the X minimum boundary is the one called the inlet. So among the inlet choices, we can use the velocity one and prescribe a 10 meters per second velocity with an hydraulic diameter that you can use around 1/2 of your size of the entire boundary. So in this case, 50 can be a good choice. Then the bounding box X max is a pressure outlet. That is the only available choice for outlet. And the default values of 1 atmosphere is good. About the Y boundaries, both min and max, we can use the so-called symmetry boundary condition. That basically means our Y boundaries, our Y sides are as far enough to consider that the variables will behave symmetrically with respect to their neighbor. So there is no influence of this boundary on the flow field. So this is a condition for both Y min and Y max. And finally, we have Z max boundary, that is the ceiling, the sky. And we can assume that the sky is far enough from our buildings that we have the undisturbed velocity flow here. And so we can assign an inlet velocity vector with the velocity along the x-axis of the same magnitude as the one in the inlet. Okay, so we are good to go about the boundary condition, and we can proceed to the simulation setting, the final section of the CFD setup. Here we have to choose the time evolution we want, and this can be considered a steady simulation. Okay. Then we have to prescribe the number of iteration and the frequency at which we want the solution to be saved. As a number of iteration, we can use 2000, for example, and save solution every 500 iterations. Okay, at this point, if you hit submit, it will run your CFD analysis, and you can just shut down your PC and come back when the analysis is complete. Again, I already had the results, so we can just go to the final section. That is the result. And maybe it's the most interesting one, since we are going to see how the flow behaves in this urban context. So when you open your case in the results section, again, the first thing to do is to choose the CFD simulation you just run, and you will see the loading of your results. First thing to do is to check the residuals. The residuals gives you an idea of the convergence of your solution. And basically, they are a measure of how far your solution is from the correct one, because the residuals measure how the equation governing the flow of motion are satisfied. And the lower the residuals, the lower the error, and so your simulation is near to the good solution. And as you can see, we have a smooth curve here, so we are clearly in a situation where our simulation has reached convergence. So now, if you want, you can also download your results in order to complete the post-processing online on your local machine. But we will do something on our local machine, and I will show you how to use ParaView. But now let's start with few post-processing online. So this is our solution. The first thing to do is to place and choose the visualization of the last step. So hit this button, the small clock, and go to the last iteration. That in our case is the 958. And let's take on our result file a slice that is basically a section that we can color with a few variables, and that will show us the values of, let's say, pressure and velocity in our domain. In order to add a slice, we have to select our file and then click on the plus button, choose the slice filter, and define the direction of the filter. So let's start with a slice with a normal along the Z axis, and with the origin on the 10 meters Z value. At this point, clicking on apply, you will see we have a section placed 10 meters above ground where pressure is shown. As you can see, this is the pressure contour showing you how in the very first buildings that face directly the wind, there is a ball of pressure, and on the back of these buildings, there is a very small value. And similar analysis can be performed for the velocity. As you can see here, we can just choose to color the slice by U, that is the velocity magnitude. And as you can see, the contour of velocity appear, highlighting the urban canyon effect in some places, and also recirculation zones around our domain. We can add as many slices as we want, just selecting our file, the main file, and adding another filter, so the slice one. This time, just define a slice along the direction of the wind, so along y, and sorry, with the normal along y, and place it on y equals to 60. Then we can hit OK, and we can see here the pressure for this vertical slice. And this is a very nice picture showing you how the pressure is very high in the front part of the building and lowers when you proceed further. So now we can color the slice with the velocity, and you will see that basically something like the opposite. So here you can find the velocity distribution. We can also turn on every slice, and you have the complete image in 3D of your contour, velocity contour. And if you also turn on the main file and zoom a little bit inside of your domain, you can see also the buildings. So complete picture with the buildings and also the slices. Okay, so now what I want to show you is a few images about the string tracer that allows you to see the trajectories of your fluid particles, as well as the contaminant dispersion. And in order to do so, I'm going to shift from the browser where we completed our simulation on my desktop, where I have ParaView, to post-process my downloaded results. So just let me switch. Okay. ParaView is an open source tool that can be downloaded from its main website. And I will show you a few tricks. Okay, so this is ParaView. I just loaded our case. When I click apply, as you can see here again, our domain. And first thing is again to go to the last step. And I can just extract the buildings. If I want to see, let's say, the pressure contour on these buildings, I can add the filter called extract block, apply it on the building, and color them by pressure. So as you can see, I have buildings with a pressure contour on them, showing how the wind interacts, causing pressure distribution on their facades. So I want to show you how to visualize the trajectories of your particles. In order to do so, we can use the string tracer, so-called string tracer. It's a filter again that integrates the velocity in your domain from a point source that I will locate, for example, on this particular point I already choose, and it's okay. You have to do some trial and error in order to find the location you want to see. And okay, and as you can see, there is a small calculation involved in this process, since ParaView has to calculate from that point source where the particles go, and this implies integrating the velocity, the local velocity, step by step to build the flow pattern. A few seconds more, and we will see how our particles move around our domain. Okay, we are almost there. Okay, so here you see the trajectories of our particles, and if you want, you can color also the streamlines with a particular variable, let's say for example U. And as you can see, along the pattern you have, along the path, the ridge, you have the color that indicates the velocity magnitude, and you will see that this behavior are not so simple to forecast. So you need to have this kind of instruments if you want to find out what's the flow path inside your area, in order to find out the characteristic structure of your field, like vortices or recirculation zones. And so this was a particular feature of this simulation. And I want to show you another one. It's really interesting, and it's contaminant dispersion in the domain. So I have to switch to another preview window. Just give me a few seconds. Okay, here we are. And again, here we have our solution file. This time it has been run with another application that is not the general one. It's the HVAC application that allows you to simulate contaminant dispersion. Again, we have to go to the last time step. And here we can extract again the block of buildings. We can color it by pressure again. And okay, we have the very similar image here. And I want to show you one thing. Behind this building on the left, there is a small building with a hole where I decided to put the source of my contaminant. That can be, let's say, smoke or industrial gases. Okay, so here you see this is the source of our contaminant. So if I want to see where this contaminant go, I can add a slice to my main file. I can use it along the normal Z and place it at 50 meters from the ground. Then I can just click apply, and I want to see on this slice not the pressure or velocity contour, but the CO contour. That is, the CO contour are the contaminant concentration. In order to see it, I have to adjust the range, and prescribing a very small value, you can see here you have a picture of your concentration. So from this slice, you can take a look at where your contaminant goes in your domain and how it is moved by the wind flow, and how it can reach some regions and some other not, maybe. So it is a very interesting tool in order to investigate where to place some critical buildings, like industrial buildings or something similar that can be related to contaminant sources. Okay, so I think that we saw quite a few features, interesting features, and we can switch back to the presentation. And finally, if you want to ask questions, I invite you to do it with the question and answer button that you can find as shown in the presentation. I can try to answer it. In the meantime, I would like you to join our website and subscribe to our welcome plan in order to start using our platform and take a look at the other webinars we performed during these days. And you will find very interesting resources like demo video or very simple guided procedures to complete simulation online. In case you need any assistance, don't hesitate to write us. We are more than happy to help you to set up your first simulations, and if our application suits your case, in case you have specific requirements, don't hesitate to contact us, because our infrastructure is really flexible and we are able to provide you custom solution very quickly. So basically, stay tuned with us, register to and follow us on LinkedIn, because we are able to custom our software to basically every need you may have, and we are really happy to do so. So if there are no questions, I want to thank you all for your attention, and I just want to wish you have a nice day.